Let's say we've got a couple of robots wandering around exploring a room. The first robot might find something interesting. Using its sensors, it can know where that object is relative to itself. But how do we know where that object is within the overall world or compared to the other robot? Now, most of us could probably figure it out with a bit of trig, but as soon as you start to have more complex scenarios, and especially when you're working in 3D, that becomes really annoying. Instead, we can use this mathematical tool called coordinate transformations, or transforms, to take care of some of the load for us. The first step is we need to assign these coordinate reference points called frames wherever we need. So here we might have a world frame, a robot 1 frame, and a robot 2 frame. In case you're not familiar, we usually use red for the X direction, green for the Y direction, and blue for Z. Next, we need to create transforms between our frames. A transform defines how you would change from one frame to another. Transforms can also be used backwards, so if we've got all this information, then we know how to change any frame into any other frame, as long as there's a continuous line of transforms between them. We can calculate what the transform would be between those two frames. To avoid running into conflicts, we want our defined transforms to form a tree structure, which means that each frame is defined with respect to only one other frame. Each frame can only have one arrow pointing into it, and so you can't have any closed loops. Mathematically, if we have a system like this where we know how to change any frame into any other frame, then we can use that to convert points or shapes or vectors between those frames. As another example, imagine we have a gripper mounted to a bench with a camera mounted above that. The camera has detected an object and we want to know where it is compared to the gripper. For this system, we might create a transform tree that looks something like this.
The first step is adjusting the camera so it's perfectly level and aligning with the center of the platform. Models has handy bubble level indicators and a center alignment line that, together with the Models platform, makes this a snap. The second step is locking the focus. We press the screen on a location close to where the laser will be hitting the object to get the cleanest line and lock the focus there. Third step is locking the exposure. We turn on the mobile device's light to artificially adjust exposure, selecting the brightest portion of the screen to get as little exposure as possible and lock it into place. As you can see, this results in a very dark picture, but once we turn the laser on, the line is remarkably crisp and clean. The fourth step is setting the platform distance, width, and laser angle. The laser angle must be as accurate as possible. Luckily, the Models platform has built-in angle markings to make this a snap as well. We're now ready to record a scan. Pressing the record button brings up an alert telling us to turn on the laser and start the platform rotating. I always try to start recording just before an easily distinguished feature, in this case one of the ears, and stop recording just after the same feature. This makes clipping much easier later. We then enter a name for our recording and the capture is complete. At this point, the Models hardware portion is complete, so I'll move to a clearer version of the software. After we've captured a scan, we need to unarchive it in order to do frame accurate clipping. This is usually a pretty quick process, but I've speeded it up for the purpose of this video. Once unarchiving is complete, we can trim the video to get a full 360-degree clip. You can move the start, end, or seek positions easily with indicators on the bottom or adjust them by dragging in the video window for more accuracy. In this case, the clip from frame 10 to 524 makes a complete 360-degree scan of the object. Models works best when it has a clear image of only the laser, so we go back into the trim view and adjust the brightness and contrast to minimize any external lights and laser reflections. Finally, we hit Analyze to extract the point information from the video frames. This may take a minute or two as well. When analysis is complete, we switch to the Models tab, click on the list icon to bring up our models list and view our new model. There are a number of different options for viewing your models. The most raw of them is the entire point cloud without any filtering. This gives you an immediate impression of how many points were captured. The next option is the Normals point cloud view, where points facing away from you are hidden. The last option is a solid view, where successive scan lines are joined together to form a solid model. Each view option also has coloring options. The first is of course solid green. The next shows successive scan lines in different colors. The one after that shows different colors based on the vertical position of the pixel in the original scan. The final one shows a laser position when scanning to help you understand where the holes in the models come from.
command. Understood. Pickup successful. Okay.
I am search of object. Now I get object's position. Now I move my arm to approach object. I move my arm to touch target. I close my hand. I move my arm to ready position.
Yeah.
I hand the lower object to my guest.
你把手伸过来，拖着手，OK。
お待たせしました。どうぞお受け取りください。 けられるんだよな。
そうですね。まあ教えれば。
キャップ開けてさ、コップにこう、ちぎりかけてさ、そうですね。こうやる。